So indeed, I'm going to continue to work towards Mirzakhani's theorem that the earthquake flow is conjugate to Horace cycle flow on the moduli space of quadratic differentials, which essentially provides a bridge from flat geometry, which is the Horace cycle flow on quadratic differentials, to hyperbolic geometry, which is earthquake flow. And the beginning of this bridge we saw already last time with the tightening map from measured foliations, which are closely related to quadratic differentials, to measured laminations, which are closely related to hyperbolic geometry. And we're going to continue today by first talking about quadratic differentials in terms of measured foliations, and then talking about earthquake flow, and I'll give a definition for you. And then finally, we're going to talk about the Horace cyclic foliation. And I'll tell you what that is, and it's really the main player in the conjugacy. OK, so to start, let's talk about quadratic differentials. So I'm going to assume you already know what a quadratic differential is. It's a holomorphic. It's something that locally looks like a holomorphic function times dz squared on a Riemann surface. And it gives you a horizontal and vertical measured foliation. And I want to understand which horizontal and vertical measured foliations you can get. And to that end, I want to define a locus called delta that lives inside of MF cross MF. And delta is going to be defined as the locus of pairs of measured foliation. So alpha is a measured foliation, beta is a measured foliation, for which there exists gamma in MF such that it has zero intersection number with both alpha and gamma. OK, so you can imagine that gamma might be a curve. And if this was a curve somehow, it manages not to cross alpha, and it doesn't cross beta either. Okay, this intersection somehow counts the number of times it's crossing the leaves of the foliation. And you could call this the locus of pairs that don't jointly fill. OK, a pair fills if it's not in here. It fills if it intersects everything else, one of the two. No foliation fills on its own because it doesn't intersect itself. Okay? The intersection number of every measured foliation with itself is 0 because everything is aligned. There's no intersection at all. So note alpha is in delta for all alpha. So you can think of this as a sort of fat diagonal. Okay, so the first lemma I want to discuss says that if Q is a quadratic differential, then I can look at its horizontal foliation and its vertical foliation. So these give two measured foliations, and this is not in delta. OK, what's the idea behind this? The idea is, well, on a quadratic differential, it gives a metric on the surface. And so somehow every curve has to intersect one foliation or the other, because a curve can't be 0 length. So that's sort of the 0th order approximation to the proof. I'll tell you the idea of the proof in a little bit more detail now. So it's a proof by contradiction. So say the intersection number of both of these foliations with some gamma is 0. And this is gamma is some measured foliation. So this is exactly what it would mean to be in delta. OK? So first, you can imagine that this was a simple closed curve. If it's not a curve, then you can approximate it by curves. So we haven't proven this, because I can't do all of the details in these 3 lectures. But every measured foliation can be approximated by curves. So pick simple closed curves, gamma converging to gamma. So weighted multi-curves. OK, and then what you'll get is that the intersection number of the horizontal part of the foliation with gamma n goes to 0. And the same for the vertical foliation. OK, so here's the horizontal foliation. And remember, one of the descriptions of intersection number we had last time for a curve and a foliation is that you write the curve as a sequence of transverse arcs, and you add up the transverse measures. OK? So this essentially, so the intersection number with the horizontal essentially measures the vertical, the sum of the vertical heights. OK, so this guy means that gamma n is or can be represented by a sequence of saddle connections with holonomy xn, yn, and the sum of the y is small. This intersection number will represent sort of the smallest you can get the sum of the y components to be for any representation of this is a sequence of saddle connections, or more generally as a path, but you won't do better with an arbitrary path. This guy will be something similar. You can represent it in a way so the sum of the xi's is small. Okay, so this means somehow you're almost, if this was 0, you'd just be following leaves of the foliation, because you can't cross them. Okay, so this means you're almost horizontal, and this means you're almost vertical. Okay, and then I'll leave it to you as an exercise to show that you actually can't have that. There's no loop on a quadratic differential that you can move in one way so that it's almost parallel to the horizontal foliation, and move in another way that's almost parallel to the vertical foliation. So that's actually a fun exercise to think about, purely in the realm of the geometry of quadratic differentials. And if you want, you can come ask me for a hint later. But that's the idea of why that's true. OK, so we get a map from the bundle of quadratic differentials to mf cross mf minus delta. And maybe I'll just make one remark before we talk about that map a little bit more. So remark, the intersection number, the horizontal part, the horizontal foliation, and the vertical foliation is the area of Q. Okay, so some of you very astutely pointed out last time that this intersection number seemed a bit like an area. And so it is actually area for quadratic differentials. OK. So now we want to understand this map. So I have a map that sends Q to the horizontal foliation and the vertical foliation is a homeo. And so it gives a map from the bundle of non-zero quadratic differentials over Teichmuller space to mf cross mf minus this fat diagonal of things that don't jointly fill. OK. So depending on your point of view, you might say that this is obvious in that for some of you, the definition of a quadratic differential is its two transverse measured foliations. The reason it's not entirely obvious is because this delta wasn't defined in terms of transversality. Okay, it's just defined in terms of these intersection numbers. And furthermore, keep in mind, MF is measured foliations up to isotopian Whitehead moves. Okay, so it might be that you have two foliations that aren't transverse, but then you can isotope them and you can somehow collapse some saddle connections or split some zeros and then make them transverse. Okay, so I want to outline a proof of this for you. I'll say proof, but as usual, it's just an outline of the proof. So we want to build an inverse to show that this is a homeo. So given two foliations in MF cross MF minus delta, we want to build Q. Okay, and the chief difficulty is getting them to be actually transverse. Okay? So away from the zeros, you want them to look like this. You have one foliation, and then another, and then at the zeros, you want them to look, I need another color here. Like that, and then once you get them actually transverse, then they just define a quadratic differential in a straightforward way. It turns out it's easier to do this actually if we go back to the realm of hyperbolic geometry, which is sort of cool. So I want to tighten H and V to laminations. So I pick some arbitrary hyperbolic metric and I tighten them to get geodesic laminations. Okay. And then I'll make a claim that H and V, which I'm now considering as laminations, I'm not going to introduce separate notation for the lamination versions of them. So H and V do not share any leaves, and each complementary region of their union is a polygon. Okay, so you might have leaves like that, and then leaves like that. And then, so a complementary region is just a connected component of the surface minus the union of the two laminations. So it might look like that, or it may also look like something like this. Or maybe, so this is if you have triangles, you might have quadrilaterals, something like that.
What would be an example where it's uniform, where it's not done with polygon? I don't see why the second part is not.
You mean why isn't the second part automatic?
Yeah.
Well, what if both of them were the same curve?
They don't share any.
So if I take h equals alpha equals a curve, then actually both parts of the claim will be false.
What is alpha? Sorry. Right, I'm saying, but if the first part is true, then what would be a picture where the second part is false?
An example of that, I'll draw it over here, would be if h is a curve and beta is a curve, but they don't fill. Then the complementary regions would correspond to the universal cover of this other part of the surface and would be quite complicated. Yeah, so I mean sort of a finite polygon, not containing any part of the boundary. Yeah, so that's an example. If one of these was and the other one was V as laminations, then they wouldn't share any leaves, but you would have complementary regions that were not finite-sided polygons. And I should say it's fairly obvious just from the definition of a lamination. In these polygons, it'll alternate a side of H, a side of V, a side of H, a side of V, just because no leaf of V intersects another leaf of V, because it's a lamination. It's a bunch of disjoint geodesics. OK, so proof of claim, although as always, it's just an outline. So if H, V share a leaf, take a weak star measure, weak star limit of measures supported on segments of that leaf to get a gamma with 0 intersection number with each of them. So the first order approximation of the proof is if they share a leaf, take the closure of that leaf. That's a lamination, and it doesn't intersect either one. Okay, then you say, well, but Alex, it should be a measured lamination, not just a lamination. So you take a Lebesgue measure on a big segment of that leaf, and you normalize it to be a probability measure. And then you take bigger and bigger segments, and then from that you build a measure on this lamination that you get as the closure of this leaf. Okay. So that's a very common thing in dynamics, where you take sort of a long orbit of a dynamical system and just average Lebesgue measure on it and take some weak star limit. So this is why they can't why leaf, and if some region of the surface minus H union V is not a polygon, find a gamma that's sort of physically disjoint from H union V. Okay, so if there's some big part of the surface that's untouched by alpha, by H and V, then you'll have a region that's not a polygon, but you could just take some geodesic in there. And similarly, you could take the closure of that geodesic, and that will give a lamination, and then you could build a measure on it, and then it's a measured lamination. Okay, but I expect you could probably even do it with gamma closed, although I haven't thought about it to make 100% sure. Okay, so this is the idea of the proof of the claim. Okay, so we know now that that H and V don't share any leaves, and the complementary regions are polygons. And the idea is now we're going to collapse again. So collapse to get Q. Okay, so what should I collapse? So you should collapse the interior of each polygon to a point, and you should also collapse each segment so I'm going to collapse that. I'm going to collapse each of these edges to a point. So this the whole closed polygon will in fact give 1 point. And when you do this, you'll get a quadratic differential. Okay, and again, this should seem a little weird if you're not used to it. But once again, I claim it's no weirder than that, that collapsing procedure I introduced on the intervals of the middle third Cantor set. And you could obtain this collapse map as follows. So you could look at some rectangle in which the two foliations are transverse. Okay, and so I'm going to just look at this one rectangle here. And let me define for you in concrete terms the collapse map there. Okay, so what I'm going to do is I'm going to pick, for every x, I'm going to pick a path gamma x from the bottom corner, just arbitrarily decide one corner as the bottom corner, to that x that's transverse to both foliations. Okay? Maybe I shouldn't call it x because that suggests one of the components, p. So I have gamma p. So then p maps to the intersection. So I first have the horizontal well, I have the vertical foliation of this path, and then the horizontal foliation of this path. So the intersection number with the horizontal foliation should give you the y component, actually. So that's why h goes here and v goes here. And it's this map which accomplishes this collapse. Okay, as you move around in each square, it doesn't change, so it collapses each square. And also, as you move along an edge, that edge gets collapsed.
I'm just confused. Is the first scenario of what you drew before the triangle?
Yeah.
That seems like a bygone.
There's no bygone here.
No. Beyond this. Yeah, on the left.
On this one?
Yes.
So there's the quadrilateral here. I mean, there would be more foliation.
No singularity is that.
It's not a singularity. That's an ordinary point.
Oh, okay.
So this, yeah, this gives a singularity, and this gives an ordinary point. Oh, so V is a measured foliation. And so its purpose in life is to give a measure to transverse arcs.
So then this is not.
So this is the transverse measure of this arc.
But you said it's a constant function. But it's really not.
It's constant inside of each square. It's not constant on this whole square, but inside of here are lots of, if you remove h and v, infinitely many squares, little squares, and on each of those little squares where the foliation don't live in the complement of the union, then it's constant. Yeah. Okay, and once again, I'll put in parentheses. So a special case, once again, is H or V has atoms. So it's once again a special case if there's some closed curve that gets positive measure one of these. Because we discussed this last time. It's if you have an atom with a closed curve that gets positive mass, then somehow you don't collapse that to make a foliation. That's a special case where really you should sort of replace that with a cylinder and then do some collapsing. Okay. So yeah, I think it's best to think about this map. And it's best to think about the case where no curve has positive transverse measure. And then this sort of local integration procedure will collapse all of this. And so this square will become an honest square. So it'll map to sort of a smaller square whose dimensions are the transverse measures. And what you'll get is a nice quadratic differential. Because then you've sort of gotten rid of all the intermediate spaces. And then you get an actual pair of transverse foliations. Okay, so there are other ways of doing it. This resorting to laminations is just one way to force the foliations to be actually transverse. If you didn't do that, you'd have to make some sort of topological argument saying you could isotope and use Whitehead moves to make them actually transverse. Okay, so let me move on now. You could take this as a black box if you want, what we've proven is the map from quadratic differentials to MF cross MF minus this locus where they don't jointly fill is a homeo. So we've understood which pairs of measured foliations come from quadratic differentials. And the bottom line is basically everything that has a hope of coming from quadratic differentials comes from quadratic differentials.
I'm confused about Whitehead loops. Quadratic differentials with zeros, so they sort of come with a preferred source, don't they?
Yes.
And now you have this map, so where you, on the right-hand side, on MF, there's an equivalence relation, so I don't know, I find it kind of confusing.
So why didn't I have to talk about Whitehead moves in the proof?
Yeah.
Because I went to measured laminations, and there's no equivalence relation on measured laminations. That was the point. It's maybe artificial. Why go to hyperbolic geometry when you start with, when you're trying to prove something that has nothing to do with hyperbolic geometry? And exactly the reason is by going to measured laminations, we don't have to worry about Whitehead moves or isotopy.
So the quadratic differential is sort of picking a preferred representative from this equivalence class as part of the definition of a measured foliation?
In a sense, but you need you need the transverse foliation also. Right? A quadratic differential is two foliations. So yeah, given two foliations, then there's a preferred version of each. But if I changed, if I replaced v with v prime, then that would sort of change the preferred realization of h. Yes, exactly. And I drew it in the case of a non-singular point, but you could, near a singular point, you could still tile it with finitely many squares, and it would just be as easy. The only case that's harder is when there's atoms, and then you have to think about that a little bit separately. Okay, so let me move on now to earthquakes. Okay, so, and my goal here is simply to tell you what an earthquake is. So here's the simplest case of an earthquake. You take a hyperbolic surface. So as I've alluded to all along, you need to have an actual hyperbolic metric on a surface. And take a simple closed geodesic. And then cut it open. Okay, and then keep track, maybe this point got glued to that point. So there's some gluing, and it identifies these 2 points. And now what you're going to do is you're going to re-glue with a twist. So re-glue with a twist by t. And this is the time t earthquake in alpha. So this is alpha. This is x to get the earthquake in T alpha of x. Okay, so when you do, these 2 points should now be a distance t from each other. And there's 2 ways you can twist. Okay, you could, reglue and twist like this, or reglue and twist like that. And this gives rise to a notion of left earthquake and right earthquake. And you just pick one, and then we're going to do either left earthquakes for all time or right earthquakes for all time. And one way to keep track of the difference is you can imagine that you have 2 people, one standing on either side of this geodesic, and they're looking at each other. And if you do one earthquake, each will see the other one move to the left. And if you do an earthquake in the other direction, each will see the other one move to the right. Okay? And so this only depends on the orientation of the surface. You don't have to pick the orientation of a curve. So anyways, we're doing either right earthquakes or left earthquakes, and it just depends on an orientation on the surface. Just a quick remark. Sorry?
Let's just decide. So which are we doing, right?
Oh, I don't care. Right, sure. Yeah. Left. Well, I mean, whatever you want. I'm not going to remember. You can try to make me decide, but I won't remember my decision. Yes?
This is different from
This is exactly a translation in Fenchel-Nielsen coordinates. So in Fenchel-Nielsen coordinates that include this alpha, this is just adding t to the twist parameter. Thank you. Okay, so if you know about Fenchel-Nielsen's, Nielsen coordinates, you understand this perfectly. Okay. Another remark is this gives a flow on Teichmuller space, which you understand if you understand Fenchel-Nielsen coordinates. If you're just adding t to one of the Fenchel-Nielsen coordinates, you're just moving in Teichmuller space. And the reason I emphasize that is people sometimes get confused about the marking. They say, oh, you've defined a new hyperbolic structure, but what about the marking? Okay, and it's especially confusing since I cut my surface apart and re-glued it. So what do I do with the marking? The observation is since I'm continuously changing the hyperbolic surface, I can keep track of the marking. Okay, and it's really no more complicated. If you understand Fenchel-Nielsen coordinates, you already implicitly understand this. Okay, and I'll also just comment, once you earthquake by an amount of time equal to the hyperbolic length, you come back at the same hyperbolic surface, but with a new marking where it's changed by a Dane twist.
Do we do it on a separating curve or a non-separating curve?
You could do it on either a separating curve or a non-separating
So
curve.
if we do it on non-separating curve, how do we reach a case that is changing the marking?
All the same, if you twist by the hyperbolic length, you'll do a Dane twist in that curve. A Dane twist even a Dane twist in a non-separating curve, that's still a non-trivial element of the mapping class group.
Yeah, that's a non-trivial element.
Yeah, that's a non-trivial element of the mapping class group. Doesn't matter if it's separating or not.
It's also a new surface, right?
It's a new surface, but once you twist by an amount equal to the hyperbolic length, it's the same hyperbolic metric, it's just a different marking.
It's the same hyperbolic metric?
If you twist by an amount equal to the hyperbolic length. Because you've just twisted once all the way around, and you're back to where you started. The same point in moduli space, a different point in Teichmuller space. Okay. Okay, so one can similarly define an earthquake in any weighted multi-curve. If you have several curves, you cut them all and you reglue them, and the amount you twist by is equal to the weight given to the multi-curve. Okay, so if I have 1 times one curve plus pi times another curve, I cut them both open. This one I twist by 1, and this one I twist by pi. Okay, so it's fairly simple. And then a general earthquake is a limit of these earthquakes in weighted multi-curves. Okay. So now if I take alpha to be an arbitrary measured lamination, the earthquake in alpha of x is defined to be some limit as I take alpha n converging to alpha n, a weighted multi-curve of the earthquake alpha n of x. Okay, so that's fine. That's a very simple formula. You now have every right to ask, and you should ask, why is that well defined? Okay, maybe you should also ask, well, Alex, you haven't proven yet that every measured lamination is a limit of weighted multi-curves, but I'm not going to prove that. Not that it's so hard. You just trust me on that. But really, what you should ask is, why is this well defined? Okay, and I don't have time to go through the details. The details you can read in. I wrote a few details in the notes, which of course are online. I encourage you to look at them. But if you want full details, there's a nice paper of Steve Kirchhoff where he does the details. Okay.
Just in 1 minute say, in what sense is everything a limit of weighted multi-curves? So you never said what is actually topology. So
The topology is the topology given by all intersection numbers. Yeah.
no, on measured lamination.
Yeah. It's the topology given by all intersection numbers is the short answer, but in a minute I'll implicitly say this is the same as another topology. As
a different topology in tabular space. I think it's the same topology in that tabular space.
there's only one topology on everything that you can use, so I just urge you not to worry about the topologies too much. You can read about them in books and check all the details, but we don't have time to go into that level of detail in these lectures. Yes?
The weight on the multi-curve, does it determine how quickly you twist?
Yes, exactly. So if I have, again, if I have two multi-curves and one has weight 1 and the other one has weight pi, to do the earthquake, I cut them both. This one I twist by 1 and reglue, and this one I twist by pi and reglue.
Is that quick isomorphism, or is something really parallel?
So actually, these more complicated earthquakes can, in a sense, be better than these simple earthquakes. Because these earthquakes give discontinuous maps. They're maps that are only defined on the complement of the curve. You get a map from one hyperbolic surface to the other. If alpha is not atomic, if it doesn't give positive weight to any closed curve, then actually you'll get a continuous map from x to E alpha x. But we're actually not going to use the maps. We just want to know which point in Teichmuller space we get.
So as a flow, if you have 1 and pi, you're doing t on one and t times pi on the other?
Yeah, yeah. But you don't really have to talk about the flow so much. If you want to do the flow, you just do earthquake and T alpha. And T alpha is just another measured lamination. So you go from the 0 measured lamination to alpha linearly. John?
You have pi and minus pi on two different curves?
No. It's a measured lamination, so it has to be positive. Only you can't assign negative weights and have it be a lamination.
Why couldn't it be a sign measured lamination?
We'll talk about that later. That gets into cataclysms, but that's just not. It's not the same as earthquakes. Somehow a cataclysm is a more radical thing than an earthquake.
So if you have two curves, both should be all right earthquake.
Yeah, you do right earthquakes everywhere, and you do left earthquakes everywhere, once and for all. You're not allowed to twist one right and one left. I mean, that's something we do in Fenchel-Nielsen coordinates. As I said, it's an example of something called a cataclysm. It's not an example of an earthquake. Okay, if you have a weighted multicurve, the weights have to be non-negative for it to give a lamination. Yeah?
So we saw that mapping that group is the isometric group of Teichmuller space with the Teichmuller distance.
Yes.
Is this like a continuous, is this also isometry? Or geodesic in?
No, this is not a geodesic, and these flows don't preserve the Teichmuller metric.
Okay.
In fact, there's nothing other than mapping classes that preserve the metric on Teichmuller space. That's a theorem of Wright.
This is just like a Horace cycle.
Yeah, this is more like a Horace cycle than a geodesic. OK, so I don't want to spend too much time on it, but I just want to give you a quick idea of why it's well defined. First of all, I want to think in the universal cover. So really, I have a measured lamination in H, and I want to define an earthquake in that. And so I have I'm not very good at drawing measured laminations. So I need, first of all, to fix one point to be, I need to pick a point and a tangent vector to be fixed by the lamination. Okay? And now I sort of have to really what I want to do is I want to cut along this geodesic and apply a translation along it to shift everything on the other side. That's the geodesic in just one geodesic, if that geodesic is given positive mass. There are two fundamental estimates that Kirchhoff proves. Not hard analysis, they're easy analysis. All you need to know is that if you have a differentiable function on a compact set, then it's Lipschitz. It's like the only estimates that's used in Kirchhoff's paper. So this it may seem like there's some analysis, but it's really, really soft and easy analysis. So you need to know, so the two estimates are, one, if you pick a point a bounded distance away from this geodesic, and then you earthquake time t in that geodesic, you move this point at most t times some constant. So earthquakes, they can move points a long distance, right? But only if they're far away from the geodesic you're moving it. And second of all, if I earthquake in this geodesic versus earthquaking in a very close by geodesic, that doesn't make a big difference. Okay, so if I'm doing an earthquake in one geodesic or an earthquake in a very slightly nearby geodesic, then that doesn't make a big difference. Okay, so what you do then is you want to define the earthquake. I'm going to define it to fix this point, and I want to know what it does to this point. And so all that matters, actually I can erase most of the lamination. All that matters is the lines between these 2 points. Okay, because whatever earthquake I do over here, that's going to shift points over here more, but it doesn't matter here. So I have this infinite sequence of geodesics. If it was finite, that would be great. That would be easy. But in general, there's some infinite sequence of geodesics between them with some measure on them. So what you do is you approximate that sequence with a finite sequence. In some way. And then you assign the appropriate mass to that finite sequence. So this sequence is like this simple closed curves. And you use this sequence instead. So to give just a tiny bit more detail, I find it helpful to draw the following picture. So I'll draw this arc that goes from the one point to the other point. So again, this point I'm defining to be fixed, and I want to know what happens to this point under the earthquake. And I have all of these infinitely many geodesics. And what I do is oh my, these are supposed to be brackets, but they're really bad. I divide the geodesic, or this arc between them, into little chunks. I drew them as sort of big, but they're very tiny. And then on each one, I replace all these geodesics with a single geodesic that goes in the same direction, and it has the same mass. Okay, and then I do that earthquake instead. And I show that's very close. And now back to the topology. I warned you I would implicitly use the fact that this intersection number topology is... so I divide up the arc from points and into these little chunks. And in each chunk, I have possibly infinitely many geodesics. And I'm going to replace them with just one. And that one geodesic should go in approximately the same direction as all of them. And it should have the mass that's the transverse measure of this arc. Okay, and then what you do is you show that actually the earthquake in this finite sequence of red geodesics does about the same thing as the earthquake in all of these. And you do that by sort of one step at a time. You transfer mass. You say, oh, I'll get rid of this geodesic and move its mass onto the geodesic. But those are almost the same geodesic. So the estimate that I mentioned before says that that's the effect of the earthquake. So there's some Lipschitz property of earthquakes that if you change the support a little bit, then it doesn't do much. And so now the topology, you can prove whatever topology you're using. It's the same as if I take a nearby earthquake, I'll get almost the same mass on each arc, each little arc, and the geodesics will go in almost the same direction. So I could pick a different approximate and still do this, and I'd get the same answer. So anyways, that's a very rough outline, but the bottom line is it comes down to 2 bits of easy analysis. One is earthquakes move points only an understandable amount. If I take a point not so far from the geodesic I'm earthquaking in, it only moves it so much. And the other one's if I replace the geodesic with a very nearby geodesic, then that doesn't affect the result of the earthquake very much. And again, both of these are very, very soft estimates. Okay, so I have a few more details than that in the notes. You can look at them. And then if you want full details, you can look at Steve's paper. Okay, so that's earthquakes. And now I want to shift gears a little bit and talk about Horace cyclic foliations, which is sort of the star of the show. Yes?
So do I understand correctly that if I fix a point, then I get a well-defined homeomorphism for every earthquake? Is that what you're saying?
then you do not get a well-defined homeomorphism for every earthquake. You only get a homeomorphism if the measured lamination is non-atomic. If you give positive measure to a leaf, then you get a discontinuity along that leaf. Like happened when you did it in a simple closed curve. So actually, there's a sense in which the simplest case, simple closed curves, is also the worst case in that you don't get a homeomorphism. And I also want to emphasize, I did all this in the universal cover, so you don't actually have to do the approximation downstairs. You can do it upstairs. So that'll actually be very important next time. All of the estimates take place in the universal cover. You don't have to pick the approximation downstairs. You can just lift and pick any sequence of geodesics between these points that approximates it, and that'll converge to the earthquake. OK, so Horace cyclic foliations are something Thurston defined. And it's first defined on an ideal triangle. So that's an ideal triangle. This lives in the hyperbolic plane. And the first thing I want to draw is I want to draw the orthogeodesics. So there's a geodesic that leaves here and goes to this point, and it's orthogonal. And that means that point you can think of as the center of this geodesic. Okay, so geodesics on their own don't have a center, they're infinite length. But if you have a triangle, each edge has a center, even if all the edges have infinite length. And these centers are just given by, there's a unique point so that if I look at the geodesic to here, this will give a right angle. OK, so that gives me these three centers. And you can show that these centers lie on Horace cycles. Okay, so if I look at the Horace cycle based at this ideal vertex through here, it'll also go through here. So then I'll also have a Horace cycle there and a Horace cycle there. And then I'm going to fill in all of the Horace cycles. So this is the Horace cyclic foliation on a triangle. On an ideal triangle. So this little bit in the middle is not foliated. Right? There's a little gap that's sort of this Horace cyclic triangle in the middle that doesn't have a foliation. But it will emerge that actually what I care about is the foliation on the boundary only, and I don't really care what's going on in the middle of the triangle. So I'll allow myself to isotope and to do whatever in the middle. So if you want, you can collapse this so that it forms a singularity. So you could take that same triangle and draw a bunch of Horace cycles. And then I have the middle points, and I could do that. And then I could just pull some of these leaves in so that I get a singular foliation. And I can do that without really changing how the leaves intersect the boundary of the triangle. So I'll only do I'll pull in and I'll affect what happens on the inside of the triangle, but I'm not affecting how the leaves intersect the boundary of the triangle. Okay, and this foliation has a measure. So it has a measure, and if I take any transverse arc, I can isotope it to an arc on the boundary, and the measure of that is just the hyperbolic length. So transverse measure equals hyperbolic length. OK. Yep.
Can you say again, how did you define the three red points?
Oh,
Are they the contact with the inscribed circle?
Yes, but the way I define them was I said that they're the points such that if you look at the geodesic from here to here, it makes a right angle here. They're where the orthogeodesics to the so it's like you drop all the perpendiculars, and it's where the perpendiculars hit the edge of the triangle.
Okay, and then the second triangle was to say how to fill in the little.
Yeah, and I just I took these with my fingers, and I just pushed in the inside until I sort of collapsed and made a singularity.
Okay, so the lines of the foliation are not geodesics.
No, they're all Horace cycles. And here they're mostly Horace cycles, except in the middle I've distorted them a little bit to make the singularity. But again, I'm not going to care so much about that. All I care about is this property, actually, that the transverse measure on the boundary is given by hyperbolic length.
May I understand it as that we can apply measure equivalence in the middle, but we cannot apply measure equivalence in the boundary?
I guess so.
Thank you.
Other questions? OK, so claim if lambda is a maximal lamination on X. So again, maximal means X minus lambda is a union of ideal triangles. Then the Horace cyclic foliations on the triangles extend to a measured foliation on X transverse to lambda. And it'll be called F lambda of X. Oh, X is a hyperbolic surface. A hyperbolic surface. So if I take a hyperbolic surface and a maximal geodesic lamination, then I can look at this foliation on each of the triangles, and they fit together to give a foliation on the surface. Okay, so I'll skip the proof of that. The proof is in the notes. It's not hard. It essentially consists of noting the foliation is the perpendicular to all of these geodesics. And if two geodesics get close to each other, then their perpendicular directions are close to agreeing. So I can fit this into a nice foliation. Yeah?
The same question as yesterday. I don't understand what would be the complement else than triangles.
Quadrilaterals, or like,
Okay.
you know, like my measured lamination could just be a single curve.
Okay.
And then the complement could be, you know, something, yeah. It could be like a whole surface with boundary. But yeah, you could also, you can have for all of the complementary regions were quadrilaterals or ideal fivegons. Yep.
It doesn't seem that the measure on that foliation depends on the measure of lambda.
Excellent observation. So remark, lambda need not have a measure. And even if it does, the measure doesn't play a role. Okay, so here lambda is an unmeasured foliation, or a foliation with a measure, or a lamination with a measure we're going to ignore. But so the measure is not important, but the fact that it's maximal is crucial. Because I only really explained how to build this in a triangle, and that's really the only situation in general where you can define it. Okay, so it somehow comes from triangles. So define MF of lambda to be the set of mu such that lambda mu is not in delta. So this is the set of measured foliations transverse to lambda. Right? Because we already know these mu are exactly the ones that can be realized exactly transversely to lambda. So in other words, this is the set of mu so that you can make a quadratic differential out of lambda in mu. Okay. So we get a map for each fixed lambda that I'll call f lambda, and it goes from space to mf of lambda. Okay, so if I use a different hyperbolic structure, I get the same Horace cyclic foliation on each triangle, but now somehow the triangles fit together in a different way, which is quite subtle to understand, and our purpose actually next will be to understand that. How can you talk about how all these finitely many triangles fit together? Given that you don't have two triangles glued to each other, there are always infinitely many leaves between every pair of triangles.
Sorry, so is f lambda a foliation that is defined by the lamination, or
F lambda x is the Horace cyclic foliation on x, arising from the maximal lamination lambda.
Wait, so is the Horace cyclic foliation or the Horace cyclic foliation?
So for each hyperbolic surface and for each maximal lamination, you get a Horace cyclic foliation on the hyperbolic surface. So if the hyperbolic surface is x and the lamination is lambda, then the Horace cyclic foliation is called f lambda of x. And it's some measured foliation which is transverse to lambda.
So why do we still have the Teichmuller space here if they totally depend on x and lambda?
Oh, it also depends on the marking.
You didn't use the marking here?
I implicitly used marking.
So how
Otherwise, you would end up in measured foliations mod the mapping class group. Like to actually get a measured foliation on a surface up to only isotopy and Whitehead. If I didn't use the marking, then I'd get a measured foliation up to a surface up to all diffeomorphisms of the surface, not just isotopy. So in other words, up to isotopy and the mapping class group and Whitehead moves. And that's a bad space. It's not as nice as just MF. Other questions? So I'm just going to take another 10 minutes and tell you a little about this map. And the main thing that we want to know is that f lambda is a homeo.
Why the domain is Teichmuller space?
Sorry?
Why the domain of lambda is the Teichmuller space?
You mean why does it depend on the marking?
Yeah.
So that's what I was just talking about. If you didn't have Teichmuller space, you'd get a map to MF mod the mapping class group. Okay, to get a measured foliation, right? MF is measured foliations only up to isotopy and Whitehead moves. If you don't have a marking, you'd get a measured foliation up to all diffeomorphisms and Whitehead moves.
No, but my question is why the domain should be some hyperbolic structure?
Oh, as opposed to?
It's the same as over there. It's f lambda of x.
I mean, I used the hyperbolic metric to define the foliation because I used Horace cycles. Does it make sense? The idea is you use Horace cycles. And because you're using Horace cycles, you're using the hyperbolic metric. Yeah, so that's for any lambda maximum, regardless of whether it has a measure. Although technically, if it doesn't have a measure, I'd need to tell you what I mean by this. But I'd need something very similar.
Parameter I use, not the twisting parameter is not used in the when you define it.
Can you? Maybe we can talk about it after. Okay. So I'll just mention, often you compose this map with a map from MF lambda to R to the 6g minus 6 that I may or may not have time to comment on, and you call the result shear coordinates. So this you could call the geometric part of shear coordinates, or maybe I'll just call it shear coordinates. And what it has to do with shears will become will become clear shortly. Okay. So to sketch a proof of this, I want to build an inverse map. Okay? So essentially the point is, as I said, in each triangle, I know exactly what this foliation is. It's just an ideal triangle. So somehow this transverse measure is telling you how to put together all the triangles and the sort of uncountably many geodesics between them, which is sort of really quite fascinating if it's the first time you've seen it. Before I build the inverse for you, first I want to have just a discussion of x and f lambda of x. Okay, so discussion of the relationship of lambda x and f lambda x. Okay, and the discussion is going to take place in the universal cover. And so what I want to think about is the following. No, I don't want to think about it that way. Okay, so I lift lambda to lambda tilde on the universal cover, and the confluent is infinitely many triangles. And essentially, I want to understand the position of those triangles. Okay, and that's going to be crucial. And essentially, what I'm going to prove is that I can figure out the position only from this transverse measure. But first, let me just assume we're starting with a hyperbolic surface to make it more concrete. And then essentially, I'll go over the whole discussion again and redo it, explaining how things work if you don't know the hyperbolic metric, but just the transverse measure.
Is that the universal cover?
So this is x tilde, and this is lambda tilde, but I haven't drawn very much of it so far. Okay, so let me just draw two triangles. I have T1 and T2. And then there's infinitely many triangles and uncountably many other leaves. Okay, so there's no such thing as the position of T1, because really it's defined up to Mobius transformations. But I could fix T1, and then I could ask what the position of T2 is. Okay, and this is what the proof's all about. And so I'll teach you how to determine the position of T1 for T2 from T1. Okay, determine position of T2 from T1. And the idea is if I can do that, then that lets me build up lambda tilde. Lambda tilde, then I can build up x, which is h mod gamma, because gamma will be the stabilizer of lambda tilde, or finite index in it. Okay. So how do I determine T2? Well, with a vector here that I'll call W naught. And then what I'm going to do is I'm going to follow a leaf of the foliation. So that's a leaf of f lambda x tilde. And let me call that mu tilde. So I follow the transverse measure, and I'll pull this along, and I get a vector here, a unit vector. So now, if I know this unit vector, I don't quite know what T2 is. Okay, so this is W. But W doesn't quite determine T2, because I could shift this vertex.
What is given to you here?
So right now I'm assuming everything is given to me, but later I'll revise the discussion.
So what do you mean then follow the measure?
So I follow a leaf. So yeah. So actually, maybe to be more concrete, let me specifically start with this vector, just because it's the nicest choice. So I'll start with the vector at the center of this edge. And then there's a leaf of the transverse foliation through it. And then I'll get to this triangle. Okay, you actually can't get to every triangle this way. But suppose that T2 is a triangle that you can reach from T1 by following a leaf of the transverse measure. Okay, so then I get this vector. And that vector is just defined to be the vector tangent to T2 that I get from following the leaf of the transverse measure. So this vector doesn't quite determine T2. It determines, so T2 has 3 vertices at infinity, and it determines 2 of them. But I could sort of shift this, and it's not determined. But there's a remaining thing called the shear that does determine it. So to define the shear, I drop this perpendicular. And I look at that red segment. Okay, and the length of that red segment, so the length of, I should give that a name, gamma. So that's what we'll call the shear between T1 and T2. So to get the shear, you start at the center of T1. You follow a transverse. You follow a leaf of the transverse foliation, and you get to here. And then you also draw an arc. And then you see what's the distance to the center of that edge. Okay, and this vector plus this shear determines T2. So let's call this vector, maybe this is W naught, and that's W. So note W plus shear determines the position of T2 relative to T1. Yep?
So generically, the blue line is a Horace cycle, right?
No. There are infinitely many bits of Horace cycle along the blue line because it crosses through infinitely many triangles.
What kind of parallel transport of some? How do you transport vectors?
There's no parallel transport. I take this point, and I follow the point until it lands here, and then I draw the vector tangent to this edge. Okay, I shouldn't have ever said the word transport. Yeah?
What if you go to the singular?
So I'm just going to assume for now that I can get to T2 from T1 without going through a singular point. So this isn't every pair of triangles. It's a good question. Yeah?
Oh, sorry, this is not a priori symmetric graph.
Shear is symmetric, it turns out. Because I could draw this. It's just sort of the defining property of a transverse measure. So I could take this red segment, and I could isotope it like this. And I could get to that segment. And that would be an isotopy through transverse arcs. So the endpoints stay on the same leaf. And that would show that at least that the shear is the same in absolute value.
You transport it, you make theta singularity, and it breaks into 2.
Okay, that's a more complicated case that I'm not going to discuss now. Yeah. Okay, so I should stop in a moment, but let me just tell you the idea now. So the idea is you want to determine the position of W from the position of W naught. And there are infinitely many triangles that it crosses through here. And I could draw these vectors, and then this would be a Horace cycle. So really, what I need to get from this vector to this vector is just a Horace cycle matrix. Okay? And so what I need to get from this vector to this vector is an infinite product of Horace cycle matrices, which has to be suitably defined. The exact definition is in the notes. So what you show is that the Mobius transformation that takes you from this vector to this vector is an infinite product of Horace cycle matrices. And you show that you can determine which Horace cycle matrices only from the transverse measure. And similarly, the shear depends only on the transverse measure. Because this hyperbolic length is nothing other than the transverse measure. Because the whole point of the Horace cyclic foliation is if you take a transverse arc along one of the edges, it just gives you the hyperbolic length. And so if you carry out this analysis carefully, it'll say, just in terms of the transverse measure, I can determine the Mobius transformation taking this to this.
But infinite sequence,
As an infinite product, which can be well defined, the definition is in the notes. If you look at in the notes, it's a very clear, precise definition of what an infinite product means. So I can determine the Mobius transformation. So that means I can determine this vector. And this is also just this is a transverse measure. So that means I can, from the position of this triangle, I can place this triangle. And maybe that's largely what I'll say about this. So what you show is from an arbitrary transverse measure, you could put down one triangle and then figure out how to put down all the other triangles. This wasn't an arbitrary pair of triangles, but you can go from any triangle to another triangle via a sequence of these. So where you can get from each triangle to the next via a leaf of the foliation. So you put down all the triangles, and then you take the closure of the set of leaves to get lambda tilde. And then lambda tilde is invariant by some Fuchsian group, and H mod that Fuchsian group is X. Okay, so I actually wrote all of this in quite a lot of detail in the notes. So if you want more detail, I urge you to look at the notes. Next time, we'll start off assuming that F lambda is a homeomorphism.
How does this prove that this is how
This builds an inverse. So I start with a transverse measure, and I put one triangle down. And then from the triangle, I figure out where to put all the other triangles. OK? And then that collection of triangles is stabilized by some Fuchsian group gamma. And then I define X to be H mod gamma. And I check that, and that X is the inverse of the transverse measure. Yeah. OK, so I'll end there for today. Thank you.